False. If A is an invertible matrix if A is row equivalent to the identity. True. True. Okay. The invertible matrix theorem applies only to what kind of matrices? N by N or square. Either one is fine. True or false? If A is invertible, then the linear transformation T of x equals AX is 1-to-1. And on to. Yes, true. Thank you. Okay, so let's take a look at the syllabus. I just want you to notice that Friday, our next class is a quiz. It'll be group quiz, individual quiz. And then after that, there's no class Monday, right, for anywhere on campus. And then I'll see you Wednesday. We're going to talk about an application of all this stuff. We're going to talk about computer graphics. Then we've got a review class and then test 1. So test 1 is going to cover everything from chapter 1 and chapter 2. No, it's not open notes. You can bring 1 page of notes with you, front and back, 8 by 11 inches, not open partners. Okay, so today is sort of the section of the book that really pulls together a lot of the ideas from chapter 1. Okay, so I just have like a little bit of really quick my notes. I'm just projecting. Basically, I just wrote out the invertible matrix theorem as my notes, right? So the invertible matrix theorem says that if A is a square n by n matrix, then the following statements are either all true or all false. So this comes in really handy because if I ask you a question from that list that's hard to answer, you can pick any other question from that list. And if you know that that question is true or false, then you know the answer to the question I actually asked you, right? So A is an invertible matrix. This is the first thing in the list. And we talked about inverse matrices last class and the way to tell if a matrix has an inverse or not. If it's 2 by 2, you can look at its determinant, AD minus BC, right? If it's 0, it's not invertible. And if it is bigger than 2 by 2, you just did like A, identity, and you try to row reduce and get them to switch. And if you don't get the identity on the left, your matrix isn't invertible. All right, which is equivalent to A can be row reduced into the identity, right? Because that's how we find inverse matrices. If you can't row reduce A into the identity, then that's equivalent to not being able to do the procedure that gets A inverse. A being able to row reduce A into the identity is equivalent to saying A has n pivot positions. Because if it's n by n, it would have to have a pivot along each diagonal, in every location of the diagonal, right? It's also equivalent to saying the equation AX equals 0 has only the trivial solution, because saying that was the definition of what? Linear independence. Yeah. If the equation AX equals 0 has only the trivial solution, that's the definition of linear independence. And the way we identified linear independence was a pivot in every column, right? Pivot in every column, right? And if you have n pivot positions in a square n by n matrix, there has to be one in every column. There'd also have to be one in every row, right? Because if it's square and you have n of them. So these 2 bullets are just saying the exact same thing, right? A is linear, the columns of A are linearly independent, and the equation AX equals 0 has only the trivial solution. And then we also said the linear transformation X goes to AX is 1-to-1. That's also pivot in every column, right? No free variables. And then the equation AX equals B has exactly 1 solution for each B in Rn. Your text buries this important result. They say at least 1, but then it's also at most 1 because it's because it's onto and 1-to-1. So it is exactly 1. The columns of A span Rn. That's because there's a pivot in every row. There'd have to be a pivot in every row if there are n pivot positions. Right? The transformation x goes to ax is onto, again, because there's a pivot in every row. There's an n by n matrix C such that C times A equals I, and then there's another one such that A times D equals I. That is the inverse, right? This just says you can find an inverse, and A transpose is also invertible. It's just a long list of equivalent statements. Remember, it only applies to square matrices. Okay. All right, so let's look at some examples. So I've got 4 matrices listed here. 2 can seem to be singular, and singular means not invertible, doesn't have an inverse, just by looking at them. Okay, which 2 do you think are singular? B and C. Why? The row of zeros, yeah. B and C. We've got a row of zeros and a column of zeros. There's no way you could ever row reduce those into the identity matrix because you'd always be missing a pivot in an important location. So B and C cannot be row reduced to the identity because of the zeros. Okay, one of the 2 remaining, A and D, you can know immediately is invertible. It has an inverse just by looking at it. D, how come? Right. So in A, that's an important thing to notice is the triangular zeros there. What does that tell you about the numbers on the diagonal? They're pivots. Yeah. So which of those matrices is invertible? A. Yeah, because it has 3 pivots. Yeah. Okay, so yeah, because also part of my notes here said that A transpose is also invertible. So an upper triangular and a lower triangular both end up having n pivots. Right. Okay, so A has n pivots. Therefore, A is invertible. 3 dots making a triangle stands for the therefore. If you continue taking math classes, you'll see it all the time. Okay, now we've got one more matrix, D. We have to figure out if it is invertible or singular. Yeah, so we don't even need to augment it. We'll just row reduce it. If you get the identity, it's invertible. Yeah. So we need to check, is A row equivalent to the identity? So I'm going to use my calculator to do it quickly. Sorry, not A, D. I'm testing D here. I don't know. I can't see it in my head. Edit. We need a 3 by 3. Okay. 1, -3, -6, 0, 4, 3, -3, 6, 0. Matrix. Math. We want a RREF. Matrix A. Get the identity. So you were able to see that without just by doing a couple of steps in your head. That's cool.
I mean, you don't really need to solve for the identity.
Yes, you also can just do enough to get 3 pivots. Yeah. Yep. Absolutely. Okay. So D is invertible. All right. If A is an n by n matrix, and the transformation T of x equals AX is 1 to 1. What else can you say about that transformation? It's onto, yep. Onto what space does it map onto? Rn. Wait, it's a superscript, right? Yeah. Rn. Okay, so here's a proof. Sort of a classic piece of linear algebra classes that you are introduced to. Proofs, we did a little bit at the beginning about even and odd kind of stuff. So I want to prove that if A is invertible, then A transpose has to also be invertible. Okay. So that's part of the invertible matrix theorem. You can't just say by the invertible matrix theorem, right? I want to prove that that is true. Verify it for myself. Okay, so what do I need to show, right? I'm given A is invertible. A is invertible. And I need to show that A transpose is invertible. So what does it mean to be invertible? Just at the most basic level. If a matrix is invertible, that means that it has... All of these things are true. But what is the definition of being invertible? It has an inverse. Yeah. And what is the definition of an inverse? It undoes the original and turns it into the identity. Okay. Okay, so if I want to show that A transpose is invertible, I have to come up with its inverse, right? I need to find, I need a matrix, I don't know, let's call it C, right? Such that C times A transpose is the identity, and so is A transpose times C. I'm going to come up with some matrix that has an inverse, right? That is the inverse of A transpose. Okay. Good question. What does anybody have a like a guess, a wild guess of what might work? Like A transpose times what will give you the identity? A inverse? Okay, let's try the inverse of A. Well, the inverse of A transpose, yeah, but that's what I'm looking for, right? Like I need just A? Okay. Do you want me to give you one to try? Well, I can't because this is for a generic A. I don't have any numbers or even any letters. I just know that A is n by n and that it's invertible. Yeah, well, we're going to prove this one little piece of it to No, because you add them too. Like you take your row, multiply by a column, right? And the things that line up get multiplied. So those are going to make the ones like you want, but then you have to add them all together.
So when you add, you throw out the other term. So you'll just get. Sure there is.
So the thing we're looking for, right? We want to find, we're looking for A transposes inverse, right?
Yeah.
We don't know that it exists, right? We're looking for A transposes inverse, right? What do we know exists? A has an inverse for sure, right? A has an inverse. So let's try A inverse transposed. What do you think? Okay, so let's see. If I multiply A transpose times A inverse transposed, I want to show that I get the identity, right? Okay, what do I do? I can't remember. Hold on. Little thing. Okay, so I want to show that A times A inverse is the identity. All right, if I take the transpose of both sides of this equation, is that allowed? Can I do that? Okay, so I'm going to take the transpose of both sides. All right, what's the transpose of the identity matrix? It's still the identity. If you make all the rows columns and columns rows, it's still going to land at the identity. Okay. How do you take the transpose of a product? Anyone remember from close? Yeah, you got to reverse the order. So it's A inverse transpose times A transpose. Hey, that's like what we wanted to show. Almost, yeah. Could I have done something that would show exactly what I wanted? Swap the A inverse and the A at the beginning. Yeah, so check. If I start with A inverse, yes, inverses multiplication is commutative. Yeah. Okay. So again, here I'm going to take the transpose of both sides. So this becomes A transpose times A inverse transpose equals the identity. That's what I wanted to show. So it just, we found a candidate with some trial and error, like of what might work as an inverse, and then we just showed that it actually is the inverse. Yeah. Oh, because this is the definition of an inverse, right? Something that you multiply A transpose by to get the identity is its inverse, right? So this thing is the inverse of A transpose. Yeah. All right, Cooper, do you want to come up and show us what you did? Oh, I think everyone would like to see it.
I want to see this. So give me a random 3x3 matrix. Any number. Do you want 1, 2, 3 to be the row or the column? I was thinking. Well, the green might win on it. All right. 5, 6, 7. 9, 1, 1. Yeah, I think I need to close the bracket.
All right, so you're trying to build its inverse?
Yeah.
Okay.
So with transposing a matrix, the great thing and why this works is these 3 positions stay the same.
Mm-hmm.
They stay the same with transposing. So if you come up with a matrix 1 over A, which happens to be 1.
Mm-hmm.
0, 0. 0's right there. 1 over 6. Then put a 0 and a 0. And then 1 over 1. Because even if you transpose this, these three positions will stay the same. They'll zero out the other columns, and you'll end up with your identity matrix of 1, 0, 0. 0, 1. 0, 0, 1. This will work.
Nope.
Why?
Oh, sorry. Okay, yeah.
No, you don't multiply. You multiply. So if I were to transpose this, it would stay the same. It would be the same matrix if I were to transpose. And if I were to transpose this, the only numbers that matter are these two. So if I were to keep these three and multiply by that, you get your identity matrix. So to do this is just 1 over
No,
8,
this isn't. When you multiply the second row times the first column, that should give you row 2, column 1's entry, and you end up with 5. Yeah. Yeah, it was a good try.